So here we are in part 2 of the video, and this is from JLab, which is somewhere. Jefferson Lab Resources, Newport News, Virginia, Thomas Jefferson National Accelerator Facility, so it's a reputable source. And they say the electron's traveling at 99% the speed of light, but in the atoms around us about 2,200 kilometers per second. So if we assume 2,200 kilometers per second for velocity right here, 2,200 kilometers per second, I took the liberty over here of making the transition, so 2,200 kilometers per second, 1,000 meters per kilometer is 2,200,000 meters per second, or 2.2 times 10 to the 6th meters per second. And of course h is still the same h that we had earlier, 6.63 times 10 to the negative 34th joules per hertz. All right, so if we do the actual calculations on this, we'll have 9.1 times 10, well, let's just do it from the top down. So 6.63 exp negative 34th. We're going to divide that by 9.1 times 10 to the negative 31st. That was kilograms, and that was a 3, not a 2. Okay, kilograms. And then we're going to divide again by 2.2 times 10 to the 6th. And so we end up with 3.3 times 10 to the negative 10th. And then the unit's a little bit weird, so let's just take a minute to talk about the units over here. If I look at the joules per hertz on the top, and then I have a kilogram meters per second on the bottom. You know that when you divide fractions, you multiply by the reciprocal. So we would say joules per hertz, and then it'd be times seconds over kilogram meters. But a joule per hertz is really a joule second. Remember, we talked about that earlier, right here, and I showed you why. So we'll just write down, instead of joules per hertz, we'll write joule seconds. So now I have joule seconds squared because it's joule seconds times seconds, and that's divided by kilogram meters. Well, we know that a joule is a Newton meter because a joule is the unit of energy or work. So work is measured in force times distance, so it's a Newton meter. So we'd have a Newton meter second squared, and that'd be divided by kilogram of meters, and look what happens, meters cancel. So now I have a Newton second squared over kilograms. But you may remember that a Newton is a force, and force is equal to mass times acceleration. So that would equal a kilogram multiplied by meters per second squared. And then that would be multiplied, second squared. And that would be multiplied by this second squared. I'll put it in a different color, make it more obvious. And that's all over kilograms. But now look what happens. Second squareds cancel. Kilograms cancel, and you just end up with meters. So our proper unit here is meters. 3.3 times 10 to the negative 10th meters. So that's the wavelength of an electron in a hydrogen atom. And if we go check out the dimension, the diameter of a hydrogen atom, we could say, what is the diameter of an atom? And let's see what we come up with. What is the diameter of an atom? Come up with a slow response, about 1 times 10 to the negative 10th. Now if you go back to what I just wrote down, it was 3 times 10 to the negative 10th. So the wavelength is in the same ballpark as the diameter of the atom, and that's how we closed class the other day, where we were saying that if we had an atom and that was the diameter of an atom, then if I had a wave going like this, and that was the wavelength, 3.3 would be 3 times this much, but the point is it's in a negative 10th. Negative 10th is in the same ballpark as the diameter of the atom. So the point is it's relevant. It's the wavelength of an electron is relevant. For us, wavelength is not a big deal, but for the electrons it is. All right. So now this is actually going to be the second of what I think is going to be 4 videos. So I'm going to stop this one.